It has no moving parts, yet it handles enough energy to power a small city. It sits silent and forgotten at the edge of town, yet it's the absolute heartbeat of our modern world. Without this machine, long-distance power grids simply wouldn't exist. Today, we're doing a technical deep dive into the static giant, the power transformer. Let's start with a first principle. We generate power at a plant, but our homes are miles away. How do we send electricity that far without massive losses? The answer is a trade. We trade current for voltage. High voltage, low current transmission loses far less energy to heat in the wires, but you can't send high voltage into your home. Something has to step it up for travel and step it down for use. That's the transformer's only job, and it works because of one man's discovery. Michael Faraday showed us you need a changing magnetic field to induce a voltage in a coil. Direct current, or DC, creates a static field. It goes nowhere. But alternating current, or AC, is like a constantly moving tide. That change is the key. It's the reason our entire grid runs on AC. Inside the transformer, we build a super efficient highway for magnetic flux called the core. The goal is linkage flux, energy that usefully couples the input and output coils. The enemy is leakage flux, energy that escapes and is wasted. The core's closed-loop design is all about maximizing linkage. But there's a bigger enemy within: eddy currents. As magnetic flux passes through conductive steel, it tries to create swirling internal currents. In a solid block, these would cook the transformer from the inside out. The ingenious solution? Don't use a solid block. The core is made from thousands of thin sheets of special silicon steel, each insulated from its neighbor. It's like a traffic jam for eddy currents. Their path is broken, resistance goes up, and efficiency is saved. Wrapped around the core are the windings, precise coils of copper or aluminum. They have a strict architecture. Low voltage windings sit closest to the grounded core as they need less insulation. High voltage windings are on the outside, where there's more space for the thick insulation they require. The rule is simple. The ratio of turns between primary and secondary coils dictates the output voltage. But handling massive current brings its own nightmare, the skin effect. At high currents, electricity tries to flow only on the surface of a conductor, wasting the interior. The solution for giant low-voltage windings is brilliant engineering, the continuously transposed cable. It's a bundle of many insulated strands that constantly change positions along the cable's length, forcing the current to distribute evenly across the entire cross-section. We're now dealing with hundreds of thousands of volts. The battlefield is the insulation system. The primary insulation isn't plastic or ceramic. It's specialized oil-impregnated paper and pressboard. Spacers made of this pressboard do double duty. They physically support the windings against tremendous magnetic forces, and they create channels or ducts for the real hero, the cooling oil. This mineral oil is a multi-tool. First, it's an insulator, far better than air, preventing arcs and corona discharge. Second, it's a coolant. Heat from the core and windings is absorbed by the oil, which rises via convection, passes through radiator fins to cool, and cycles back down. This is a closed, life-sustaining loop. Keeping it cool is non-negotiable because paper insulation degrades irreversibly with heat. The grid isn't static. Demand surges at dinner time, causing voltage to sag. The transformer has a brain to handle this: voltage regulation via tap changing. The logic is beautifully mechanical. To raise output voltage, you add more turns to the winding. To lower it, you remove turns. These taps are on the high voltage side, where the current is lower, making switching easier. And the most advanced ones can do this without cutting power, using an on-load tap changer, a complex switchgear that seamlessly reroutes current mid-flow. But how does 400,000 volts get into the oil-filled tank without flashing over? A simple wire through the grounded steel tank would create a deadly arc. The solution is a condenser bushing. Inside its porcelain shell, layers of conductive foil create a series of capacitors. This forces the insane external voltage to drop in perfectly uniform, manageable steps down to ground potential. It's a voltage ladder. Finally, the real-world scale. Industrial power uses 3 phases, offset by 120 degrees. Instead of 3 separate transformers, we combine them into one ultra-efficient unit with a 3-limb core. The connections matter. Delta on the high-voltage transmission side for stability, and star or Y on the distribution side, which provides us with the crucial neutral or ground connection that makes our household power safe. So, from the laminated silicon steel core that tames magnetic flux, to the windings that outsmart the skin effect, the oil paper insulation that contains lightning, and the intelligent tap changer that stabilizes our grid, every component serves one master: efficiency. This silent, static giant doesn't just handle electricity, it sculpts it. It shapes the raw, chaotic output of generation into a precise, usable form that can travel continents and then safely enter our homes. With efficiencies often over 99%, it is one of the most perfect machines ever built. It is the invisible backbone of civilization.